Welcome to this edition of Lakeside Physics. In this video, we will introduce you to the concept of conservation of energy. According to Richard Feynman, conservation, the conservation law, means this, that there is a number which you can calculate at one moment, and as nature undergoes its multitude of changes, this number doesn't change. That is, if you calculate again this quantity, it'll be the same as it was before. An example is the conservation of energy. There's a quantity that you can calculate according to a certain rule, and it comes out the same answer after, no matter what happens. Conservation of energy states that the total amount of energy in the universe since its creation has remained constant. If energy appears to disappear, it didn't actually disappear, it just changed forms. While we do not know why it is true, it has been proven true again and again. According to Keith Snodgrass Klingler, it is perhaps the most powerful idea in all of science. Conservation of mechanical energy deals with the idea that mechanical energy can be conserved or changed if there's work done. So recall from previous discussions that the mechanical energy is the combination of gravitational potential energy, elastic potential energy, and kinetic energy. If there were other types of potential energies, these would go in there too. For example, chemical or electrical. But for our purposes for now, we will just deal with GPE, EPE, and KE. To account for outside influences, we will use the concept of work. Work will add or remove mechanical energy from the system. We will call this external work, or WEXT. So note that when work is done by the gravitational force and the spring force, the total mechanical energy does not change, just the individual values of GPE and EPE, and subsequently KE. Therefore, no work term is needed for the work done by these forces. So, kind of in conclusion, what we're saying here is that the initial mechanical energy plus the work done on the system is equal to the final mechanical energy. Another way to state this is that E initial plus WEXT is equal to E final. Now note, an example of an external work done would be, say, friction. Friction is taking energy out of the system, so you would have a negative work term in there that would change the total mechanical energy. So let's consider the steps. First, write down what you are trying to find. Pick a before and after. Choose a place where you know the energy and the place where you want to know something. Pick a GPE equals 0 line. This is arbitrary. Be strategic. Often we will pick the lowest point in a problem to be your GPE equals 0 line. Write down your equation. The E initial plus work external equals the energy final. And for each time, for my initial time and my final time, consider if there is gravitational potential energy, kinetic energy, or elastic potential energy. If there's any external work, you'll have a term per external force or influence. You want to make sure that you keep track of your signs. So if it's adding energy into the system, you'd have it positive. If it was something like friction or air resistance, it would be removing energy and there would be a negative term. And then solve. So let's try some example problems. In this example problem, we have a 2 kilogram box is dropped from rest at a distance of 20 meters above the ground. Now, what is the speed of the box immediately before it hits the ground? Well, this doesn't seem all that interesting. We've already solved this type of problem before. We can use kinematics. Let's go ahead and solve it using kinematics. We're trying to find the final velocity. We know the initial velocity is 0, our acceleration is going to be negative g, and our displacement is negative 20 meters. So if we use the fourth kinematic equation, we can solve and we get a final velocity of negative 20 meters per second, or that it has a speed of 20.0 meters per second. Now let's instead consider this problem using conservation of energy. So again, we're trying to find the final velocity right before it hits the ground. We can use the idea that the initial energy plus any work done by external forces is equal to the final energy. In this particular case, we're going to pick our GPE equals 0 to be the ground, the bottom of our situation. A will be our initial position and B is our final position. And so if we consider the initial position at A, there is only gravitational potential energy. At B, there is only kinetic energy. There was no work done by external forces because the only force acting on the object was gravity, which we said was already roped up into the gravitational potential energy. So we just have that the GPE initial should be equal to the KE final. We can plug in the values we know and solve, and we get that the final speed is 20 meters per second. If the mass of the box were doubled, what would happen to the box's speed? Well, if we go back to our equation that we started with, we can actually see that we plugged in a mass, but we didn't need to. The masses cancel, so the speed would still remain 20 meters per second. Glad it did, because in our kinematic equations, we don't have anything that would show a difference with mass. A 2-kilogram box starting from rest slides down a frictionless incline with a measurement shown below. Now we want to find the speed of the box immediately before it hits the ground. In many ways this problem seems similar. We have a 2-kilogram box starting at a height of 20 meters, but now it's sliding down an incline. So if we use energy to solve, we can find the initial velocity, the initial energy plus the work done by external forces is equal to the final. Again, we'll consider our GPE equals 0 line to be the lowest position. And in doing this, we end up that initially it had gravitational potential energy, it wasn't moving, so there wasn't any kinetic energy, and at the end, when it gets down to the bottom, the gravitational potential energy is 0, and we just have kinetic energy. Now we want to pause for a moment and consider whether or not there was any work done by external forces. If we were to draw a free body diagram, we have no friction, we have force of gravity, which again we said we don't need to worry about in terms of work done, and we have the normal force. So there is a force that we might need to consider. However, the normal force is always perpendicular to the motion, so it does no work. So we have no work external term. So we can go ahead and solve, and we get 20 meters per second. Note that even though this is a different situation, we still end up with the same speed in the end. Think about how we would have had to solve this problem if we were using kinematics. We would have had to use forces to find the acceleration and then go ahead and solve a kinematic equation. Now using energy, we end up with being able to solve this problem in a much quicker, simpler way. Alright, let's do a third example. A 2-kilogram box starting from rest slides along a frictionless roller coaster-like track as shown below. Assume g equals 10.0 meters per second squared. What is the speed at the bottom of the track? So we want to find the final speed. We will again use our conservation of mechanical energy equation and say that the initial energy plus any work done by external forces is equal to the final energy. We pick our GPE equals 0 line to be the bottom of the track, and we consider whether or not there's any work done by external forces. Again, since there is no friction, we can assume no air resistance. The only two forces acting on the block are the force of gravity and the normal force. Now note that the normal force changes throughout the track, therefore the acceleration is going to change throughout the track. But the normal force is always perpendicular to the motion at any given moment in time. So since the force is perpendicular, it does no work. So in the beginning we just have gravitational potential energy, and when we get down to point B at the end we just have kinetic energy. So we can solve, and just as our previous two problems, we end up that the final speed is 20 meters per second. Now notice that this takes an almost impossible force and kinematics problem, and it makes it really easy. Our acceleration is constantly changing. We wouldn't be able to just do a straightforward calculation with forces and kinematics. Let's do one more example. A 65-kilogram skier initially traveling at 9 meters per second moves across a frictionless snow and then up to the top of a 3.5 meter tall hill. Again, assume g equals 10 meters per second squared. What is the skier's speed at the top of the hill? So we're essentially looking for the final speed at point B. We'll consider point A to be our initial position and point B to be our final position. Again, we can look at our initial energy plus the work done by external forces equals our final energy. Since there is no friction, no air resistance, we only have normal force acting, but as we've stated before, this normal force is always perpendicular to the motion. We can just assume that we have no work done by external forces. So we have our GPE equals 0 line at the bottom, and we end up with an equation that says the initial kinetic energy is equal to, at the top, some gravitational potential energy plus some final kinetic energy. We can go ahead and plug in the information we know and solve for the final speed. We get 3.3 meters per second. Again, just to make it perfectly clear, this would have been a problem that was nearly impossible to do using forces and kinematic equation, and becomes very simple using this concept of conservation of mechanical energy. Also note that we gave you the mass, but the mass was not necessary at all. If you look at it, it's in each term, and the masses would have canceled out, and we'd still get 3.3 meters per second, no matter what the mass of the skier is. So that ends our video for today. Notice that all of the problems that we did were situations in which there was no work done by external forces. So the mechanical energy was conserved. It was the same before as it was after, and it was just converting from different types, looking at kinetic energy and gravitational potential energy. In future videos, we will look at when there actually is work done by external forces, such as friction or air resistance, or possibly a push that gives it energy or takes away energy. I hope this was helpful. Please let us know if you have any questions. Thanks.